Awesome. So, hello everyone. Thank you for joining us today for another Astro webinar in Aura. And special thanks to our speaker, Sam Cutler, for accepting our invitation to be here today with us. We really appreciate it. Thank you, Sam. And so Sam Cutler, for a little bit of background, Sam is a PhD candidate in University of Massachusetts Amherst, working with Kate Whitaker on Quiescent Galaxies. Correct me if I'm wrong. And today he's gonna talk about low mass quiescent galaxy. We are all eager to hear more on that, so the stage is yours.
All right, thank you so much for the introduction. Yeah, I'm Sam Cutler. I'm a sixth year PhD student at UMass Amherst. I work with Kate Whitaker, John Weaver, and the rest of the primer and uncover teams on all things galaxy evolution. But today I'm particularly going to be talking about low mass quiescent galaxies and what makes them so interesting. So, for kind of a quick overview, I'll start by talking about galaxy formation and quenching on the whole. Um, Specifically, then transitioning into quenching at low masses, why it's so difficult to study, and then how we're solving that with WST. Um, and then I'll transition to the projects we've been working on recently, looking at the size and structure of these low mass quiescent galaxies, what this tells us about how they form, and then where we'll head in the future. So starting off with kind of a broad overview of galaxy quenching. Um, for as long as galaxy evolution has been around, the study of galaxy evolution, we've noticed locally there's this really strong bimodality in the population of galaxies, where you have going all the way back to the Hubble tuning fork between elliptical and spiral galaxies. Um, there's been this dichotomy morphology. We've also seen it in the colors of these galaxies, where these ellipticals tend to be a lot redder than the blue spiral galaxies. And this has led to a lot of different measurements that have shown up throughout galaxy evolution over the years, such as the color magnitude diagram or UVJ selections. And so this has been crucial to galaxy evolution as well. And then the one that's most important to what I'm going to be talking about today is the bimodality in star formation, where at least locally these elliptical galaxies have much lower rates of star formation, much less interstellar gas being the fuel for star formation, whereas spirals have more gas and higher rates of star formation. And so this has led to a lot of kind of standard paradigms like the star forming main sequence, where now you have a selection that gives you kind of this main sequence of spiral galaxies, whereas you have your red dead elliptical galaxies below the main sequence. And for a while, this perplexed astronomers, even going back to the 1980s and 90s. We didn't know why elliptical galaxies and spirals look different. And so this is kind of a diagram showing the thought at the time where maybe if you form a lot more stars earlier and they're a lot more massive in elliptical galaxies, this creates more supernova early on, and that supernova feedback is what clears the gas out and makes the galaxy stop forming stars, whereas spirals have a more constant, slow rate of star formation. We know now this is largely wrong, but it kind of shows that coming up with ideas for how to quench these galaxies has been an active area of study for a long time in galaxy evolution. And so on that note, I'll transition to talking about quenching as a whole. Um, just starting with looking at the quiescent fraction as a function of cosmic time. A large fraction of galaxies start to become quiescent, and the epoch known as cosmic noon from redshifts of about 1 to 3. At a redshift of 1, uh, over half of all massive galaxies are quiescent, and significant fractions of lower mass galaxies are quiescent as well. This is happening despite at the same epoch, there's the highest global rates of star formation in that we know of in the universe's history. And so there's a lot of star formation and there's a lot of available gas, yet we still see more and more galaxies have stopped forming their stars. And so this is a very interesting kind of contradiction that's happening in the universe at this epoch. So how and why do galaxies quench? I really like to show these two kind of diagrams because they talk about all the different mechanisms that we've come up with to quench galaxies, and they also break them down into different categories to kind of simplify everything. And I'll go through this a lot more in detail in a second. But what I want to point out now is that both of these seem to highlight mass as a big component in why galaxies form and why galaxies quench. And so that makes quenching things with not a lot of mass very difficult because if mass is a big component, obviously low mass galaxies aren't going to be able to quench via those mechanisms. So why is quenching without these mass-based mechanisms difficult? Well, starting off with things like gas inflow and gas cooling, if you shut off the flow of gas into the galaxy from its surrounding circumgalactic medium, or if you prevent that gas in the circumgalactic medium from cooling and being able to be accreted by the galaxy, you shut off your chance of creating future stars. So once all the gas in the galaxy is consumed in star formation, if you don't get future gas from around the galaxy, you can't form more stars. And this can happen through shock heating, where if the galaxy gets really massive, the gas in the CGM will be heated to the point where it can't be accreted efficiently. Also, things like feedback from both AGN and stars can heat the CGM and prevent that gas from accreting as well. But this is difficult at low masses because shock heating requires galaxies to be very massive, with halo masses of almost 10 to the 12. And even as you go back to higher redshifts, you can have cold streams of CGM gas within this overall hot CGM accreting. So shock heating is really only good at explaining quiescent galaxies that are very massive and below redshifts of around 2. And things like AGN and stellar feedback, while they can explain at least temporary quenching events by heating the CGM, they're kind of self-limiting where if a galaxy has heated its CGM and shut off future gas inflow, if it consumes all the gas within it in the AGN or in star formation, then those feedback mechanisms turn off. And so you're able to reaccrete gas again once the CGM is cooled and restart the process. And so you have to have kind of some combination of these two to quench galaxies. You could also prevent the gas that's already in the galaxy from forming new stars. And this is mainly done by stabilizing the gas and preventing it from efficiently collapsing into giant molecular clouds and star forming regions. And the main reason that's thought of is that could do this is by morphological quenching. So if you form a bulge or a bar or some kind of really massive structure in a galaxy, that can stabilize the gas in the disk and prevent it from collapsing and forming new stars. Um, However, bulge mass is very strongly correlated with the overall mass of the galaxy. So this is just showing the fraction of the bulge fraction within galaxies as a function of stellar mass. And you don't really see significant classical bulges until a mass of about 10 to the 10, and even pseudo bulges until a mass of about 10 to the 9. So if you want to quench lower mass galaxies, they probably won't be quenching via morphological quenching mechanisms. Uh, you could also remove the gas from the galaxy. You could eject it, or you could consume it very rapidly in a burst of star formation or something like that. However, again, this kind of comes back to the fact that it's only a temporary solution. If you consume all the gas, you can still accrete more gas from the CGM and resume star formation in the future. And this is a really nice diagram I like to show from Sandro Tochello, where it kind of illustrates this process where a galaxy will undergo, say, a central starburst, causing it to become this compact blue nugget. Then, because that galaxy has consumed a lot of the available gas within it, it'll undergo a quenching event when that gas is depleted, taking it below the main sequence. As long as that galaxy is at either high enough redshifts or if it's below that shock heating halo mass, it can resume accreting gas from CGM and repeat this cycle until it either becomes massive enough or it's late enough in the universe. And this is something that we've found by studying some of these kind of middle of the main sequence star-forming galaxies, so around masses of 10 to the 9 to 10 to the 10.5. Um, a lot of them show signs of central starbursts. However, there's no other indication that these galaxies are quenching. So even though they're experiencing a very strong central starburst that should consume a lot of their gas, they're not actively quenching from that, and they should resume star formation in the future. So you might notice I didn't mention anything in the environment column when I was walking through these diagrams. And that's because environment is actually a really good way to potentially quench these low mass galaxies because in environmental quenching through interactions with other galaxies, you can remove either the interstellar medium or the circumgalactic medium or both. And in doing so, you permanently quench the galaxy. It can't accrete more gas. It can't form future generations of stars. However, this requires a galaxy with a very hot, dense intercluster medium, and mostly clusters that are virialized. And so these are only really found at redshifts of below 2. And so you're much more likely to find low mass Quiescent galaxies at lower redshifts. We want to see if we can find them at high redshifts. And do we even expect to see them is kind of the first question here. So we have this current paradigm where there's two major pathways to quenching galaxies. Um, Mass quenching, in which processes that correlate very strongly with the mass of a galaxy work to halt star formation, your formation of a bulge, AGN, um, or just building up your overall massive halo. Those can all shut off star formation. And then the other side, you have environmental quenching, where you're basically just stripping gas from a galaxy in a cluster or protocluster environment. And so low mass galaxies aren't massive enough for mass quenching, of course, and cluster redshifts or cluster environments at higher redshifts haven't had enough time to form. And so this makes it kind of difficult to find these cosmic new and low mass quiescent galaxies. So as a quick aside, why do we care about low mass quiescent galaxies at all? They don't make up, the bulk of the mass in the universe. Um, but I think there's a few very interesting things. So for one, there's this kind of potential missing link between in the overall process of massive galaxy formation. And so, as we understand massive galaxies, they need to form via mergers. You need to form, a massive elliptical, and that requires mergers that change the structure of the galaxy. These mergers need to be gas-free so that you can really expand the size, and this leads to the steeper shape of the quiescent size-mass relation. These are also called dry mergers. And they also need to be minor mergers because that also leads to a steeper growth in the size of galaxies. And so the ideal candidate for a minor gas-free merger is a low mass quiescent galaxy. Another reason is simply because most of the galaxies in the universe are low mass. And so we really want to understand the overall process of galaxy formation. We need to cover the entire parameter space of the mass function. Another reason is that until now, essentially, we haven't been able to detect low mass quiescent galaxies at redshifts greater than 1. And so this is really unique parameter space that we're able to probe in the era of JWST. And the reason is because in normal kind of surveys with astronomy, we have this wedding cake strategy to observations where you start with shallow, very wide area surveys and then work your way up to deep, kind of pencil thin surveys. And the goal here is to essentially cover the entire mass function. So because massive galaxies are more rare, but they're brighter, you should be able to get a significant sample of them with a shallow, wide area survey. However, low mass galaxies are very faint, but there's a lot of them. So you don't need as much area to get a significant amount, but you do need very high depth to do that. When we're talking about low mass quiescent galaxies, this goes out the window because they're both rare and faint, especially at higher redshifts. And so you need data that has both significant area and depth. And so this is what we've been trying to do with some of these JWST treasury surveys, in particular Primer and Uncover. These are the three fields here. Uncover covers the Abell 2744 lensing cluster on the left, and then In the center and right, I'm showing the two primer fields, which cover the Cosmos and UDS legacy fields. And so to give you kind of a better sense of the overall depth and area of these surveys, uh, first I'll start by showing where we were in the area of HST. So, there's very wide but shallow surveys like 3D Dash, or you have your very deep surveys like the Hubble Deep Field or the Hubble Frontier Fields. And then also on here is Cosmos Web, which is the largest JWST Treasury survey right now. And if we move towards the JWST area, you can see just how much improvement there's been. So Cosmos Web, which is fairly high up in this HST plot, is now at the bottom, and Hubble Frontier Fields is in the same place. So even Uncover gets over a magnitude deeper than the Hubble Frontier Fields while covering more area. And Primer also covers about 10 times the area while also being just as deep as the Hubble Frontier Fields. And so using these surveys, we can then start to study low mass quiescent galaxies in depth, and this is leads us into the two projects that we've been working on recently. So again, returning to the HST era, since around 2015, we knew that, or some HST observations began to indicate that the quiescent size mass relation started to flatten as you move to lower stellar masses. And so um, from Kate Whitaker's 2017 paper. You can see it around a mass of 10 to the 10 or slightly lower, that size mass relation is really flattening at a size of about a kiloparsec. Same thing in Kalina and Kova's 2021 paper. And these get down to much lower masses. And you can still see that flattening is present there. And then we were able to see the same thing in 2022 from the Cosmos Dash survey. However, um, when you try to go to higher redshifts, is this flattening real and is it still present? Because there's a few different factors that bring it into question. One is that the depth of HST surveys limits these studies of low mass galaxies to really redshifts less than one. As we go to redshifts greater than one, we really don't have a significant sample between masses around 9 to 10, 10 to the 9 to 10 to the 10 solar masses. There's also the resolution. In F-160, HST has a resolution of about a kiloparsec or so, and that gets worse as you go to higher redshifts. So at these redshifts, this flattening sits right at around the full with half max of the HSC PSF, which makes it difficult to determine if it's a real effect or if there's some bias in our size measurements. And then lastly, HST only covers out to about 1.6 microns, which at these redshifts is really only covering kind of the rest optical, which means we're subject to outshining. And outshining basically just means that we want to probe the bulk of the mass in the galaxy. And to do that, you need to probe redder wavelengths where the lower mass stars emit. If you probe shorter wavelengths, you'll basically just see the massive stars because they're so much brighter, and so you won't be actually getting the equivalent of a mass weighted measurement. And of course, JWST is perfect for solving all of these problems. We have much higher depth, we have better resolution, and it goes to redder wavelengths. And so we can solve all these problems with JWST observations. And so this is what we did. We created a sample of low mass quiescent galaxies in a combined uncover and primer field. We did this using an extended UVJ selection because the standard UVJ selection misses a lot of these lower mass galaxies. We also invoked a criterion on the specific star formation rate, and you can kind of see some of these galaxies in the inset are crossed out. Those are ones that had star formation rates that weren't consistent with a quiescent galaxy, and so that reduced our sample as well. We also broke these into three separate subsamples based on the stellar age of the galaxy. So between 30 and 100 megayears for this youngest sample, an intermediate sample between 100 and 500 million years, and then an older sample greater than about half a gig a year. we measure the size for all these galaxies and put them on the size mass relation. And what jumps out right away is that this flattening, while it's still there, it looks a lot more like almost two disjoint relations. And so if we kind of sketch it up, um, we can really see that low mass quiescent galaxies are forming a distinct population at cosmic noon. And if I just overlay kind of a mock-up of the star forming size mass relation, you can see that these low mass quiescent galaxies are much more similar in size to star forming galaxies. And just so it's a little more clear from the data, this is a result that just recently came out from Masih Hamadouche, a postdoc at UMass. And she found that, again, there's these two separate relations. But if I overlay her star forming relation on this, you can see that it overlaps a lot with the low mass quiescent galaxies and that they're just slightly smaller. So that's a good confirmation of these results as well. There's also this kind of region between the two populations where there's not a lot of quiescent galaxies from about 10 to the 9.5 to 10 to the 10.3. If I kind of blow up this histogram I have on the side of the figure, you can see that a lot better, where between these masses, there's just not a lot of galaxies. And this lines up really nicely with this dip in the quiescent mass function, in this case from John Weaver's 2023 paper. And so this is a good confirmation that this kind of lack of galaxies in this mass regime is a physical effect and isn't due to any selection biases in our sample. We also measure structural parameters for these galaxies to kind of understand, are they primarily disks or spheroids? And you can again see there's this really stark difference between the low mass and massive galaxies, where these low mass galaxies have much lower Sirsic index, something you would expect from a disky galaxy where the light is a lot more evenly spread out, while the massive galaxies have higher Sirsic index, where they'll be very centrally concentrated with very faint wings, which is what you'd expect from a spheroid. There's a similar kind of difference in the axis ratio, but you see it a lot better when you look at the full distribution of these structural parameters, especially with the structural ones. Again, the Sirsic index, you can really see that these younger low mass galaxies have a lot lower Sirsic index, whereas the more massive older ones have a higher Sirsic index. But in the axis ratio, we can actually break these down and see intrinsically what kind of morphology these populations have. And this is what an undergrad at UMass, Aisha Abdullah, did. Aisha basically modeled these axis ratio distributions to figure out what the population is composed of, what percent of disks, spheroids, etc. And from this, we found that these low mass galaxies are primarily disky, whereas the massive galaxies are primarily spheroidal. And so this really, again, ties into the fact that these low mass galaxies are very similar to star-forming galaxies, despite having no appreciable amounts of star formation. So how do we interpret these results? If these low mass galaxies are very similar in structure and in size to star-forming galaxies, however, their quenching must leave them largely intact. It's not significantly disrupting their morphology. They're still looking like star-forming galaxies. And so again, this kind of nicely ties into this idea of environmental quenching at low masses and mass quenching at high masses, where you're not affecting the structure very much at low masses. At high masses, you're leading to compaction, where if you build up a bulge or if you're just forming a lot of mass to mass quench a galaxy. And it also really nicely ties into this picture of how galaxies grow in size from Peter Van Dokkum's 2015 paper, where low mass galaxies, their growth is dominated by star formation. That's why they look like star forming galaxies. And so, when they quench, they should also appear like they've been growing to the star formation. When you get to the massive end, the growth is dominated by mergers, especially minor gas-free mergers, and that's why you see these galaxies are elliptical and have a lot larger sizes. There's one caveat to this. When we look at the age distribution, especially as a function of mass, we see that most of these low mass quiescent galaxies are younger than about 500 million years. And so is this some kind of bias in our sample against sources these, these very faint red sources? Or are we possibly seeing some of the first instances of low mass quenching, and that's why we don't see any that are older? If these are the first galaxies in the universe to quench at these masses, then perhaps there's none that are older than this. And so this is what we'll try and tackle in the next project. One option could also be that these aren't actually fully quenched. And so a lot of simulations and now observations recently with JUC have kind of highlighted that low mass quiescent galaxies, especially at high redshifts, have very bursty star formation histories. And if you catch one of these galaxies at this low point in the star formation history, it can really masquerade as a quiescent galaxy, both in terms of the spectrum and the color. And so these mini quench galaxies, and they're also called napping galaxies or smoldering galaxies in the literature, are a potential contaminant in the sample and could explain a lot of about this population as well. And I'll tackle this again at the end of the second project as well. So yeah, if you look at where the our low mass quiescent galaxies lie in the UVJ diagram and where a lot of these mini quench galaxies are expected to lie, you can see it's possible that there is some overlap here. So how many of our galaxies are actually fully quenched? And so this leads us to the next project, where now we're trying to look at low mass quiescent galaxies in a known cluster environment. In this case, in Abell 2744 itself. Um, what does the size mass relation look like, especially compared to both this high Z sample and to field samples at a similar redshift? And then also, when did these low mass quiescent galaxies in Abell 2744 form and quench? And can we kind of tie them to this high redshift sample and establish some sort of evolutionary history? Um, so to do this, because it's so low redshift and we don't have a ton of shorter wavelength complement here, um, we have to use this color magnitude diagram selection where we're selecting the red sequence here to pick out cluster members, um, quiescent cluster members, and then also pairing it with a redshift selection to make sure we get galaxies that are significantly low redshift to be a part of the cluster. This sample also has a full complement of now medium band data from the medium band mega science project, as well as spectrophotometric data from the second cycle of or the second phase of the Uncover project. And so you can see these blue stars here are highlighting sources that have associated near spectroscopy. And so this will give us a really good opportunity to get really robust star formation histories, and I'll talk about that more later. So again, we put these on the cluster size mass relation here, and I put a few field samples on there as well. The red one is from Massey's paper. The kind of the darker maroon one is from a sample of local dwarf spheroidals, or sorry, local dwarf galaxies. And in both of them, we see a lot flatter size mass relation than what those samples find. And you can't see here because I'm just showing the relations, but our scatter is also much larger than what these studies find as well. And so, is this potentially an issue with completeness or sample selection? Um, Maybe these surveys can't get to as low redshift because they're in a field and not a cluster. Or is this some real physical effect where potentially galaxies that have entered the cluster later are larger than those that are in there later, and this is kind of leading to a flattening of the size mass relation. And I'll talk about that more as we move forward. So again, the structural parameters show, at least in terms of the Sersic index, show a similar story to the cosmic noon sample. They all have Sersic index of around 1. But the axis ratios are notably higher. If you remember, the median axis ratio from the cosmic noon sample was around zero point 0.5 to zero point 0.6. Well, these are mostly at 0.7. And again, if we look at the distribution of these, we can now see how different it is. So the color lines here are from the cosmic noon sample, and the shaded region is from this cluster sample. And so it's a lot more strongly peaked at the high axis ratio end compared to these flatter ones for the low mass galaxies. And again, when we try to figure out the intrinsic populations of these, we see that um, this population is a lot more consistent with spheroidal galaxies compared to the low mass one galaxies at higher redshift being more spirals. So we think this is mostly a population of dwarf elliptical galaxies, especially given the fact that they have a lower Sirsic index than what you'd expect from an elliptical galaxy. The next thing, and I mentioned this earlier, is we want to take these star formation rates and project back in time to see what they looked like at cosmic noon. And so here I'm just showing this is our higher redshift sample. Um, this is our sample from the cluster. And so there's definitely some evolution in the star formation rate since then. I'll just put on some simulations for comparison. And then for that sample with the associated spectroscopy, we can get these really robust star formation histories and trace them back in redshift to cosmic noon. And so what we see is already by redshift of 2, these galaxies are all quenched, especially if we look at the simulations. And they have similar star formation rates to the Quiescent galaxies at cosmic noon. We do the same thing in mass, and what we find is that at least at a mass of around 10 to the 8 to 10 to the 9, most of these galaxies have similar masses to those at cosmic noon. And so it's possible that these galaxies um, are progenitors of these galaxies. The reason why I limit the mass range to only 10 to the 8, 10 to the 9 is because at higher masses in our cluster sample, because these galaxies are so nearby, they're so bright, and they have a very complex morphology. A lot of times when you're detecting them, they get shredded and broken up into a bunch of different sources, and so it's hard to get a really complete sample at that end. Meanwhile, as you go to higher redshifts, these galaxies are just faint, and so it's hard to get a lot of them in a complete sample below a mass of around 10 to the 8. And so this is why that mass range is so limited that we're looking at. The last thing we do is look at when they formed in terms of their formation redshift, when they quenched, and again above a mass of about 10 to the 8, most of these galaxies seem to form at redshifts of 2 to 4, which is where we also see our cosmic noon sample form. And so again, this is all really good evidence that there is some potential evolutionary link between this cosmic noon sample of quiescent galaxies and the ones we see in a cluster at lower redshift. So what does this mean for the overall story of how we form and quench low mass galaxies? This the first thing that happens, or that we speculate that happens, is at cosmic noon when these first virialized environments with dense enough intercluster medium start to form. You start to quench these low mass galaxies via ram pressure stripping or some other cluster effects that don't cause a lot of significant morphological change, at least on shorter timescales, and leave some residual gas and star formation rate in the center. So this is why these galaxies are mostly disky and why they have a slightly higher star formation rate, still quenched, although this is kind of a transitionary regime where it's only about zero point 0.5 to zero point 0.7 dex below the main sequence. Um, we also find that 75% of our sample at redshift 2 to 3, um, at least for the uncover sample, um, are associated with a known redshift 2.5 overdensity behind Abel 2744. However, another uncovered collaborator looked at this overdensity and also didn't see any signs of environmental quenching. So it's still a bit of an open debate. The second piece of the puzzle is that once these galaxies are quenched and in a cluster environment, there will be continued cluster interactions and effects that alter their morphology, remove residual gas, and basically make them look like what they look like today. So this can result in galaxies that are more elliptical, as the kind of more loosely bound stellar material in the outskirts is removed by harassment from other galaxies, by continued tidal effects, and then when this residual gas in the center is also removed or consumed in star formation, you result in a much lower star formation history, which brings us down to where what we see today. Um, Another thought is that galaxies will continue to be accreted into the cluster environment, forming a new generation of quiescent galaxies. However, because these just enter the cluster environment, they should have larger sizes and look more like the sample that we saw at high redshift. And so this could explain why our scatter is much larger here, and why the size mass relation is much flatter than what we see in the field. So what can we do in the future, going forward, to really flesh out these ideas? One is to get stellar population modeling for our whole sample of Able 2744. We only did this for the sources that had associated spectroscopy. However, with the medium bands, we should have enough resolution to at least get a sense of the age of these galaxies. And so we should be able to see if there's an age gradient across the size mass relation. We tried to do this with kind of a more basic modeling. This is showing the difference in specific star formation rate above and below the size mass relation, but as you can tell, there's not much difference. Although, if we look at the lowest and highest specific star formation rate quartiles, we can see that um, the things with really low specific star formation rate seem to have a kind of a longer tail in their statistical index and be concentrated at higher axis ratios. So, there is some evidence there, but getting really robust ages will go a long way into confirming this or not. And then the second idea is to look at low mass quiescent galaxies at kind of a shorter, a more nearby redshift, and see if we see older low mass quiescent galaxies in those populations. So see if we see anything in this region here. If we do, this is good evidence that the reason why we didn't see them at higher redshifts is because low mass quenching began around redshift 2. If we don't, though, it could be evidence that those that we saw at higher redshift were just mini quenched galaxies, and they'll turn back on their star formation back on and won't show up in as a quenched population at lower redshifts. And so to summarize, um, at cosmic noon, quiescent galaxies fall into these two main classes. You have your young, low mass disk-like galaxies, and then the old massive spheroids. In Able 2744, we see that low mass quiescent galaxies have a much flatter size mass relation, are more spheroidal than what we saw at cosmic noon, despite forming at similar redshifts and having similar stellar population parameters. And so the overall picture that we see is that environmental quenching begins around cosmic noon, which quenches these low mass galaxies, and then continued morphological changes um, as they interact with the cluster environment lead to this population of mixed disks that are younger and have entered the cluster more recently, and then dwarf ellipticals that have been in there much longer. And so this is very unrelated, but it's too cool not to mention. We have a cycle 3 proposal that was accepted to look at this galaxy called the Relic. The Relic is a redshift 2.5 massive quiescent galaxy that was found on a cover. There's a photometry only paper out on it from um, Kate Whitaker. And what's really cool about the Relic is that it has these visible globular clusters within it. all the way out at redshift 2.5. And if you subtract the galaxy, you can see them really well there. There's also some evidence of tidal interactions with nearby companion galaxies. You can see that some of the globular clusters are blue, while some is red, so there's an age gradient in them, which if you look at globular clusters locally, they're all at least 10 billion years old. And so you don't really see that until you go to higher and higher redshifts. And so we're hoping with this IFU data, we can really get a sense of the age of these galaxies and kind of figure out how globular clusters play a role in the overall formation of massive quiescent galaxies. So I guess this is related in that we're now probing galaxy formation or the components of massive galaxy formation to lower and lower masses. And so this is very preliminary, but I just want to say a huge thank you to Nagin and then also the rest of the Beast team. I think it includes Fiza, Sina, and Lauren, who've been working with John Whitaker on making IFU not so much of a headache. And so thank you all, thank you to them. This is our rough reduction of the IFU. Here is one of those kind of blue younger globular clusters. This one is one that we believe is in Able 2744 itself. And so if I just run through this IFU cube, you can see really, really robust detections of O3. There's also one kind of right above it that also has a detection right here. H alpha, and then really cool, we have even some sense that these globular clusters might have helium-1 detection in them. Um, and on that note, I will take any questions. Thank you so much for listening.
Okay, thank you so much for sharing all this amazing work with us. It was really exciting to see your IFU data. I was just hearing from John about it, that it has a good progress, but it's so exciting. Thank you for sharing. We have time for questions. Uh, could you please go back to the IFU data on the relic that you showed us? I am a bit confused about the place of the IFU on your galaxy.
Here,
I see.
um,
Could you talk about your dithering, or how did you get your data for the IFU data on your galaxy here?
yeah, so um, we have basically two pointings. We have this main kind of 30-minute exposure on the galaxy itself. It's a really bright galaxy, so we don't need a ton to get to a significant signal to noise. But that's just to kind of get a sense of what the stellar population of the host galaxy looks like. And then hopefully we can model that out because the globular clusters will have light contamination from the host galaxy as well. So if we want to do any stellar population modeling with their spectrum, we need to remove the impact of the host galaxy. And then we have this deep, almost 20-hour exposure to get enough signal to noise on the individual globular clusters itself. Um, the I had to rotate it here because the IFU is in the detector plane as opposed to having north be up like in this one. So yeah, I basically just took the zoom in and rotated it to match up these two sources in there.
Yeah, I was a bit worried about your background, that when it's on your target galaxy, you don't get that much of a background. So I was like, what's going on? What do you want to do? How do you want to do?
Yeah, so
But it's okay.
so there is kind of a grouped observation. So there's also a pointing here that's not on the host. And so those are kind of grouped together. So hopefully that should help us get a sense of the background, at least for the host galaxy.
Awesome. Thank you. So we have people online. Is there any questions? You can raise your hand. We have time for other questions. Okay, awesome. So let's thank Sam Cutler and Thank you. Thank you for joining us today.